The American Society of Civil Engineers has given the United States a grade of D for our infrastructure. But why? The roads look good enough, right? Bridges are in a way a lot like icebergs. We only see the top 10% of icebergs, and the bulk is hiding underneath the water. Similarly, a great many deal of problems we have on bridges are caused by what we can't see. The most severe of these is known as scour. My name is Kyle Sanford. I'm a commercial diver, an underwater bridge inspector, and a sophomore civil engineer student here at Clemson. And today I'm going to talk to you about what scour is, the implications of scour, and how we monitor it. According to the National Highway Institute, scour is defined as the removal and transportation of materials from the bed and banks of rivers and streams as the result of erosive action of flowing water. Through the last few weeks in our geology classes, we have been learning about the causes and results of physical weathering, and in reality, this is no different. Basically, the flow of water picks up and moves rocks and sediment from the channel bottom and moves it elsewhere. This isn't exactly rocket science. We all know that water is powerful and can move things around. What's interesting and intricate about scour behavior is the fluid kinematics behind the scenes. Without going into too much detail, we can define fluid mechanics as the field of physics and mechanics concerned with the movement of fluids and the specific forces required to create the movement. So, one thing we have to monitor as bridge inspectors and engineers is how the design of a substructure of a bridge will affect the natural flow of a waterway and how that flow will impact the structural integrity of the bridge placed. Objects placed into a waterway create areas of higher and lower pressure. In the field we call these areas of low pressure eddies. We generally see these eddies directly downstream of an object. As you can see in the image, the water is moving from upstream to downstream, is forced to travel in a longer path around the substructure unit. This causes areas of high pressure on the lateral faces of the submerged object, and thus increase the flow rate around. The equal and opposite reaction to this is to create an area of low pressure and lower flow around the downstream fascia, right here. You can see as the flow continues to move, it gets sucked into the substructure unit before it gets caught back up by the rest of the waterway. Right there. In this next clip, we're going to watch a quick excerpt from a search and rescue swimmer training video which clearly shows the low pressure area of an eddy created by swift moving water around a boulder in the waterway. You can see as he swims into the eddy how it forces him backwards, even with the raging water on all sides. You may be wondering how eddies contribute to the scour of a waterway. It's actually really simple, and actually I had to make this next image in CAD to demonstrate my point here. Here you can see a simple log at the bottom of a waterway. The flow is moving from left to right, and as the flow creates that low pressure eddy on the downstream face, the water begins to dig down into the sediment and kicks it up into the waterway for it to be moved further downstream. What's pretty interesting about this example is how you see where the effect of the eddy will eventually lead to an increase in speed of scouring just downstream of the log. The increased flow rate of the water over the eddy will cause the downstream bank to begin undercutting right around here. As it begins to cut this channel back, it will create a steeper slope on this side. You can see the effect of this on top of the water actually, and we call it upwelling. In the next video we can see a whole lot going on in the way of fluid kinematics. And if anyone has taken that class and I'm wrong at any point, please stop me. But what I see happening here is that we have a large region of shallow water closer to the shore, and a region of comparably much deeper water towards the center of the channel. In this deeper region, the depth of the channel actually varies considerably from here to here. You can see the water beginning to upwell and circle back just around the downstream of the peninsula. This water coming up is what looks like plumes, and that's our upwelling. What makes these areas of upwelling particularly interesting for the bridge inspector or engineer is that if there are periods of upwelling, it means that the sediment removed from the channel bottom is getting kicked up higher into the waterway, carrying it further downstream. One of the best visual indicators of scour is called aggradation, which is the result of this upwelling. And aggradation so all of that sediment that's being eaten away has to go somewhere, right? On bridges that have underground scour, we often see these areas of sand, silt, or clay built up above the mean water line directly downstream from the bridge. As you can see in this image, the waterway is flowing from right to left, and all this sediment that's getting washed up from underneath the bridge is being pushed downstream, and whenever you get a high water event, that means that that sediment that's coming from upstream is settling just downstream, which makes sense. If you go over a bridge that commonly experiences high water, you'll see something to this effect usually. And if you see a whole lot of it, that's a good indication that scouring is happening on the bridge. So what kind of effect does scour have on bridges? Well, a substantial one actually. The Underwater Bridge Inspection Reference Manual names scour as the most common cause of bridge failure. In order to explain why, we will briefly examine the most common type of substructure, which is the footing on top of pilings. You can see here, the bridge is set on top of these footings here, which help spread out the force of the bridge on the channel bottom. These footings are set on top of pilings, which add additional stability to the structure by utilizing what we call skin friction. So the deeper that these piles are, the more friction from the surrounding earth is causing, which keeps it steady in place, and it makes it really hard to sink down or move laterally or shear. This is called skin friction. Generally, these pilings will go extremely deep in the ground. The deeper the piling is, the deeper the skin friction. It's pretty common to see these pounded 60 feet or deeper into the channel bottom. The problem is that the water doesn't seem to care how deep these pilings go. In this first example, you can clearly see a footing here which was formed very poorly. If it wasn't formed poorly, it looks like it may have had some sort of impact damage that caused a lot of it to be eaten away. But what's more important here is that you can actually see the piling underneath the footing, which means that this is starting to get some undercut. Whenever bridges get to this point, they're called scour critical, which basically means that the bridge has proven to undergo scour. In this next example, let's see, you can clearly see the piles. This is definitely a scour critical bridge. Actually, if me or my team were inspecting this bridge, we would close it because this needs to be immediately rectified. This isn't something that you can fix with any scour countermeasures. There's already enough of these pilings exposed that it can cause the bridge to actually fall over. So if scour on a bridge is so important, you may now be wondering how we monitor bridges for the progression of scour. And we do this in three major ways. One is a scour analysis, two is an underwater inspection, and three is ultrasonic imaging. The first is that if there is a bridge in constant heavy flow or in a waterway shaped such a way to encourage scouring, the United States Geological Service will perform a scour analysis. on the structure to determine the likely effects the waterway will have on the structure over a set period of time. I really couldn't find a good graphic for this because in general these reports are very long and mostly consist of numerical values that take into account average velocity of the waterway, bottom material of the channel, and all of this information gets put through a computer program to estimate how much scour will occur on a bridge over a set course of time. The second way, which also happens to be my favorite, is underwater bridge inspection. An underwater bridge inspection is required on all bridges at a maximum of a 5-year interval. Divers enter the water and we take measurements at the bottom to gauge if scour has impeded the bridge in any way. This is actually me in the water just before doing a bridge inspection, and you can see some guys here tethered who are going down to check out the bottom. The third way we monitor it is by ultrasonic imaging, which is a really neat thing. Thanks to breakthroughs in technology, we are now able to get these high-resolution images through a process known as side-scan sonar. Inspectors will position a rotating sonar transceiver in an appropriate position adjacent to the substructure unit, and then high and low frequency sound waves will be emitted by the transceiver. The time for the echo of these sounds to come back can give us a distance, which a computer then puts into an image like this, showing us where everything is happening. And on this bridge in particular, you can see how the channel bottom started out at this elevation and has changed. Now, whenever we go through scale drawings of these, we can actually measure roughly how much sediment has been washed away. So it's actually a really important, awesome new tool that we have. In conclusion, it's important to remember that while oftentimes you are unable to see the effects of scour, I can assure you it does exist. The grade given to the United States infrastructure is commonly dismissed due to the fact that a large amount of the degradation lies below the waterline. It's important for us to all have a basic understanding of the geological process due to its very real impact on our infrastructure. It is more important for aspiring civil engineers and geologists to have a thorough understanding of scouring due to the inherent need of innovation in combating its effects on our infrastructure. Thank you.